Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's a great pleasure to introduce Suvrit. Suvrit, he is a faculty member at MIT right now, and before this he had a couple of small short stints at CMU and Berkeley, and before that he was a research staff member at MPI Tübingen, and before that he did his PhD at UT Austin with Inderjit Dhillon and BTech at BITS Pilani. So it's my pleasure to have Suvrit here, and you have the mic. And he will tell us a lot about large-scale optimization.
Okay. Thanks, Pratik, for the introduction, and thanks to all the organizers for inviting me. First time I have now the pleasure to be at IISc Bangalore. Really nice to be here. And I'm going to talk about, the first lecture that I'm going to talk about will cover more fundamentals related to, it's basically to establish some of the notation that we will see again in the second lecture related to large-scale optimization. So the first lecture is just giving some concrete background. Many of the things may be familiar to several people in the audience, so just bear with me if there is repetition of knowledge. Many of the things may not be familiar to, however, everybody. So I'd like to first spend some time establishing that background knowledge, and then later, it could easily happen right now because of some miscalculation in my mind, that my lecture, instead of ending at exactly 12:30, I may have to spend 10 to 15 extra minutes, but hopefully not more than that. But I'm warning you in advance in case you had urgent lunch plans or something. So the course material I will put apart from the summer school website, they will have links to all the material. I will put the course material related to my lectures on that website. That URL is not yet functioning, but all this material will show up there. And these are hyperlinks. You can click them in the PDF. And some of the standard reference books and the full semester long courses based on from which this material has been derived, they are linked here. The lecture slides and material there is much more detailed in case you want to look at related material. So essentially this is my only slide where I list explicit references. I'm not going to have a list of references at the end of my lecture slides anywhere. So you may want to, if you're interested, visit these URLs and check out the recommended books and papers and other things on this topic. There's a lot of information there. And the kind of things I'm going to talk about, they lie, many of these things lie at the foundation of optimization related work published at top machine learning conferences. So I just listed some of the venues. This is not all inclusive, like I have, say for example, I forgot to write KDD in there and so on. But these are some of the venues where the material that I'm talking about today, if you are interested in what's the cutting edge of research related to the material that I'm talking about today, you will find many of those related papers in these venues. So that's kind of the background. So the plan for today is, the first lecture is mostly a super fast kind of recap on some basics of convexity and convex optimization. And those basics are important so that later I can just use them without having to explain them. And after we've gone through those, so the red thing is what I'm going to talk right now. And some of it may, hopefully it doesn't overflow more than 15 minutes. Because of that, there might be slightly more material in the slides than I'm going to fully speak about, but I decided to leave that material in there for the people who like to look back at the slides for reference. So the slides are sort of, they have all the information there for you. And later I'll move on to first order optimization methods, proximal methods, etc. Those are our first brush with simple large-scale optimization methods, but still not truly large-scale. And tomorrow I will talk about the currently popular truly large-scale optimization methods, with leading on to maybe I'll speak some words about methods that then also work in parallel and distributed settings. If I get time, unfortunately there is not enough time to talk about everything. I will try to tell you about some words on non-convex optimization. So the bulk of the material I'm talking about is focused on convex optimization, but that's because it's easier and more convenient to get some deeper theoretical understanding of the material. But algorithmically, the algorithms that you'll see, they are not limited to work in the convex setting. You can also apply them to more general problems, and people do that. For example, in the current popular deep learning business, the kinds of optimization techniques that I'm going to talk about now, very similar techniques are the ones that have been programmed for those things. And of course, the theoretically interesting thing is, many of the theorems and proofs that we see today and tomorrow, can we have similar or related theoretical understanding for those more difficult problems? A special important case of such non-convex problems where you do have theoretical proofs, Pratik has already covered that, but it's a rich world of problems. So okay, that was basically the introduction. So let's dive straight into recalling some basic concepts, and feel free to ask me a question in between, but it may also be even better for you, if you're really interested in the details, to catch me later, maybe during the lunch break, if you want to talk about more details. So super fast, I'll go through some basics of convex analysis and some other concepts that come up moving from convex analysis to convex optimization. So this is just the mathematical background. So we begin with concept of a convex set. Convex set, and we are going to limit our attention to convex sets in Euclidean space, so just in vector space, R to the n. And there, essentially a convex set is a set which contains all its line segments. And that's just what the picture is saying. That's the formal definition, that if x and y are in the set, then the line segment between x and y is also in that set. Interestingly, that's the standard definition. An interesting thing to know is that convexity, maybe people thought about it as a generalization to the idea of linear combinations, because people started looking at vectors and doing, say, linear algebra with those objects, and then when you have vectors, you take a linear combination that you see in first year undergraduate when you study linear algebra. I take linear combination, and the scalars that with which I combine the vectors, those scalars can be anything in the base field which is real numbers. If I put additional restrictions on those scalars, the amount of algebraic power gets reduced, but somehow more refined geometric structure appears, which we can try to talk about. So if you put the restriction that the scalars combining coefficients are non-negative and add up to 1, you get convex sets. If you drop this restriction that they have to add up to 1, but you only require non-negativity, that's called a conic combination. So just saying that I'm just giving you pre-digested concepts, but if you wish to think about how these concepts may have arisen, or how you could generalize them if you wanted to, if you want to essentially think of whatever I'm telling you today, if you wish to approach it with a research mentality that you want to break the axioms and the rules with which we are constructing this analysis and optimization, where are the important things that you could change to discover new structure? But anyhow, that's just the spirit of it. So I'll accelerate soon. And some very important theorems related to convex sets. So we defined what is a convex set, and starting with one convex set, you'd like to construct other convex sets. And already in advance, I can tell you the reason why we are interested in studying convexity is that it's easier, sort of easier, to solve convex optimization problems. And that's the reason we like to understand convexity further. Easier and practically useful, of course. So this is a basic theorem, intersection of two convex sets is convex. And with this theorem, you can verify convexity of a vast number of convex sets that you see in applications. Just this simple theorem which you can prove in one line. I'll show you an example of that. So these are some sets like the interval or the line, some kind of polygon or some other polyhedron with hyperplanes or a cone of positive definite matrices, etc. There are some convex sets. Other examples, and during my talk, there are many times you will see the word exercise. So at least for all the students in my audience, I encourage you to try to solve that exercise on your own. Once you solve that exercise on your own, you'll understand everything way better. So I marked out some interesting exercises for you to try out in case you haven't tried out before. And I'll already give you an answer to, say, this one. This is when you're doing linear programming, for example, or quadratic programming, like in support vector machines. You have constraints of this form, linear inequalities and linear equalities. This set is convex. As soon as you've shown that a half space is convex, to show that, just use the definition. What is this? This is just an intersection of lots of those half spaces, essentially. And by the intersection theorem, that is convex. So already linear programming with such constraints or falls within your ability to analyze, right? So that theorem, intersection theorem, is by far one of the most important. A distinguished type of convex set is called a convex cone. It's just, maybe I'll just draw it for you here. A convex set which essentially contains all of this. So it contains non-negative multiples of all the vectors in the set. Okay, here is a challenge for those of you who think convex sets are usually easy to understand. Here is a challenge for the more advanced listeners in my audience. A and B are symmetric n by n matrices. The tuple of those real numbers generated is a compact convex set. So it's a subset of the plane, and to prove that it's a compact convex set is a non-trivial exercise. It has been subject of several papers back in the day. It's just closed and bounded. So just because we are in finite dimensional space or whatever, just think it's closed. Closed means it contains all its boundary points, and it is bounded. No. See this interval. Well, okay. See this interval 0 to infinity. It's not upper bounded, but okay, it's not closed either. So, oh, I'm just naming that set. I just gave that set a name. Yeah. I just wanted to give that set some name.
What is the set name? No, not that. What explanation? It just generates resulted.
So if you look at it, all that does is it contains of numbers of this form. So that set contains x transpose Ax is a real number, and x transpose Bx is also a real number. So it contains of pairs like that. For all x, as x, for all x that have inner product equal to 1. So you have an infinite number of such x's. you look at all possible pairs that arise, and the collection of all those pairs is a convex set. Okay, anyhow, this is a challenge problem. Let's not spend time solving it right now, but I encourage you to think about it. It's a this challenge problem lies at the heart of a lot of very important optimization problems. So once you have convex sets, then the next important concept for us is that of a convex function. Convex functions are defined over convex sets. So essentially for us to really talk about a convex function, the domain should be a convex set. So that's why we started with a convex set. And this is on an interval, we just say a function is midpoint convex if it satisfies this inequality. So the way I like to read this inequality is function f at the arithmetic mean of x and y is smaller than the arithmetic mean of f at x and y. That's why this is called the arithmetic mean convexity. And more generally, this is the definition that not only with x plus y by 2, but with all possible fractional combinations, you have that inequality. That's the more general definition of convexity. And if this is usually called Jensen's inequality, and Jensen proved in 1905 in his famous paper that if function is continuous, then it is convex if and only if it is midpoint convex. So I wrote this version here because many times if you're trying to do by hand and verify convexity, it's it kind of turns out to be easier to do that. So I usually like to just verify that and ensure continuity, and you're done. So that's our definition of convex functions, and I'm going to mostly give some examples of some very interesting convex functions that come up in convex optimization. And for those of you who like to see pictures, here is a diagram of a convex function which you may have seen before. Convex function essentially, that's the arithmetic inequality that at the line spanned by the endpoints, the function always lies below the line. That's one way to look at it. An alternative way, which we'll actually come back to after maybe 20 minutes, is not through just definition in terms of the value of f of x, but in terms of tangents at different points. So convex functions are curved upwards like that, so at every point they have a tangent, so they are always bigger than some linear function at every point. I'll make that more precise later on. And there's a third geometric view, pictorial view of convex functions, which is also useful. So all these three are useful when trying to verify convexity or think about it. So the third one is that for convex functions, the slopes increase monotonically as you go from one end to the other. So here PQ has this negative slope, then PR has higher slope, and then QR has even higher slope. So think of slope as a signed number, right? So the slope here will be so it just monotonically increases as you move along this curve. So those are just three geometric views of convex functions. And monotonically increasing slope for differentiable functions is the same thing as second derivative being non-negative, right? So that's a standard well-known way to verify convexity. So this is just a picture of that. Okay, one of the most important ways of constructing convex functions is this theorem or this example. Because remember, the reason I'm talking about convex functions is because we will see later or soon enough, for many machine learning problems or for many statistics problems, the problem of estimating or solving a model involves solving a convex optimization problem. So we'd like to understand these creatures. And we said, okay, we somehow talk about convex sets, but the challenge problem already showed you that it's not always trivial to verify that a certain set is convex. We usually just construct them to be convex. Similarly, we defined a convex function, but just because I defined the concept of a convex function, it won't help you so much until you have access to a bunch of tools that allow you to detect convex functions and to construct them. Numerically, you can never guarantee that a given function is convex, because numerically you cannot verify even continuity, right? Because computer works with finite precision. Continuity is a real number concept. So we won't worry about the numerical version, but I've given you a class of functions which I claim is nice for optimization, but any nice class of functions that you construct is nice only if we know how to construct members of this class. And this is one of the most important ways to construct members in that class, is if you have a function f which for each fixed value of y, so f is a function of two variables. I'll show you an example of this soon enough. If f is a function of two variables, for each fixed value of y as a function of the remaining variable x, it is convex. Then you take the maximum over all possible choices of y, then that function remains convex. By hand, verifying this is pretty direct, because all you have to do is just try to verify the standard inequality. So you can just try to verify this and use the fact that this is the max. So you should be able to verify this pretty quickly. Another thing is, if you have a function written in terms of some vectors, and if you make a linear transformation, linear transformations are friends of convexity, they don't ruin convexity. So these two things are kind of very basic and very important, and pretty much the cover 50% of what we need to know how to construct convex functions for the purpose of these lectures. A more non-trivial result is that if you minimize function of two variables, even under minimization, this is a very nice property. So minimization is like eliminating some variables. So if you have a function of two variables and it is convex in both variables, and you eliminate some by minimizing them out, then what remains is still convex. And I'm showing it slightly abstractly now. Pretty soon you will see an application, a very simple application of this powerful looking theorem. So the proof is on the slides, you don't have to worry about it. I'm just leaving it there for future consumption when you refer to the slides. But it's a very important property, because what it means is, if you have a function of several variables and it's convex in all variables, you can reduce the number of variables by minimizing some of them out, and maybe the remaining, and then working with the remaining object. So that's one of the benefits of this, that this doesn't destroy convexity. But it's crucial that it be, the original thing had better be convex in the pair together. Otherwise this doesn't hold, as you may have seen from an alternating minimization example, that those things are convex not in the pair, just individually. So this is making a much stronger assumption but giving a stronger conclusion.
So instead of infimum, shall we put supremum delete convex, right?
Yeah,
Let's say
yeah,
as from
yeah. That's the so the previous one I wrote with max, but actually it works with sup.
for any y.
Yeah,
Y is any set.
yeah. Y is arbitrary. That's the beauty. So this thing, as a function of y, f can be crazy. This one requires f to be well behaved with both x and y. So there's a difference. Yeah. The first, I'll show you a nice application of this thing also. We are coming to that. I'm looking at some interesting convex functions. So this harmless looking or harmful, depending on your perspective, looking function is one of the nicest convex functions in my opinion. So this function allows us to associate a natural membership function for every convex set. So you say that I have an indicator function. If for a convex set, this function outputs 0 if evaluated at something that lies inside the set, otherwise it outputs infinity. So trying to minimize such a function, what does trying to minimize an indicator function mean? Trying to minimize an indicator function means being able to pick one point in your convex set. Any point will do. So that already shows you that convex optimization problem can have infinite number of solutions. If your set has infinite number of points in it, which it has to, then minimizing this will, any feasible point will do. But this is a very important function. Here it's only for the notation. So henceforth, please remember, I will use this notation few times. And this is a very important function. Okay, so here's an example of the infimum theorem in action. So if X is a convex set, so if this is script X, this is a convex set, you want to find distance to that set. So X happens to be some point which lies outside your convex set, and you want to find the length. How far is this X from the convex set? So the value of this distance, which as you can geometrically see, you will have to make an orthogonal projection. I will also write that formally again. The length of this distance, that is called the distance function to a convex set. That distance function is convex. Proof, the proof follows by using the previous two results. X minus y is jointly convex in X comma y. And if you want to see it super explicitly, X minus y, so if your original vector is z is xy, then X minus y can be obtained by multiplying it with this matrix. So this is a linear transformation, and we saw that under linear transformations things remain convex. Of course, I formally didn't yet prove that notation of a norm is convex, but you can believe that. So it's jointly convex in X and Y, and we are minimizing simultaneously. Hence, by our previous theorem, the distance function is convex. So this is a way to use that theorem. This is a very basic object that pops up in convex optimization. I should have shown this earlier, but a class of convex functions that you will encounter again and again, have probably already encountered several times, are this distinguished class of convex functions called norms. So a function that satisfies these properties, if it's non-negative and it is positive definite, that means it is 0 if and only if its argument is 0. If to this function you send in an argument that is not exactly the 0 vector, it will output a positive number. And it satisfies this positive homogeneity, that is, if you scale the vector, then the value of the norm just gets scaled in absolute value by that scalar. And the most important one, it satisfies subadditivity, just like a triangle inequality type inequality. So if you have a function that satisfies these properties, we are just saying we are investigating functions that satisfy these properties, such functions are called norms. And they are extremely important functions. They even happen to have, that's why, their own notation. We usually don't denote, rather than using f, we use these double bars. And you can verify these are convex by just the definition. That value, you can check as an exercise which of my axioms it violates. If you want the answer already, I don't want to make it a spoiler, but it violates one of these axioms, maybe more than one. You can check which one. So they abuse that notation, so one should be careful and call it a quasi-norm. It sort of looks norm-like-ish, that's why people call it a norm. Later you'll see, I think, in a later lecture you'll see much deeper insight between why people may still call it a quasi-norm, but it is not a norm. It's not convex either. So because otherwise it would violate this theorem that I wrote here, norms are convex, which you should try to prove. Okay, some norms you may have seen. Euclidean norm, LP norms, p equal to 1 is probably the most popular, and sometimes p is equal to infinity. That is obtained by taking limit of this thing as p goes to infinity, and you can check when the limit of p goes to infinity, the contribution is only of the largest guy in there, so that's called the L infinity norm. So these are defined for strictly for p less than infinity, and for infinity you take a limit. The other popular one which you may have seen by now a few times is the Frobenius norm. It looks at matrix as a big array of numbers and treats it like a vector and takes the vector norm. More for matrices, there is another norm called the operator norm, which is the largest singular value of a matrix. That's another norm. And verifying this may require some effort, but these are like some standard convex norms that we encounter now and then in machine learning. So the next very important convex function, which is motivated by the max theorem. So I told you that the max of arbitrary family of convex functions is a convex function. Here is a special case of that theorem, the so-called Fenchel conjugate. This was, I forget the year, but Werner Fenchel wrote a very influential 5-page long paper in which he introduced this Fenchel conjugate, sometime I think in the 40s. And it's an application of that max theorem because it's taking pointwise supremum over x. It says f star of z is convex function. And the nice thing is, because of that max theorem actually, so this is just the definition, okay? Because of that max theorem, the f in here can be anything. This f doesn't have to be convex for the f star to be convex. Because in the max theorem, just as you pointed out, in the max theorem, as a function of y, the thing could be arbitrary. So here we are taking maximizing over x, so the function of x can be crazy, but what comes out is just pointwise maximization of convex function of z, because it's linear in z. Hence, the product that comes out is convex. But this is one of the most important convex functions that exists. And it's very important because it opens up a dual view, a different way of looking at convex functions. And that different way we've actually already looked at, but I'm going to come to it soon. Example, plus infinity and minus infinity are conjugate to each other. The most trivial, probably not so interesting conjugate function, but it's setting the boundary lines. I've left another exercise in here just to show you how to exercise some of the concepts developed. Don't worry about absorbing the proof right now, but I have left it in there when you later hopefully look at my slides to see that up till slide number 20, the concepts that have been developed, how you could use them to prove these examples. Couple more interesting Fenchel conjugates. So if you have a quadratic function, x transpose ax, where A is a positive definite matrix, then its conjugate is just given by A inverse, Z transpose A inverse Z. And that's an exercise worth solving. This is the hinge loss kind of thing that you see in SVMs. For that we have a very nice conjugate. And I'm just writing the examples there, but for those who have not seen such material before, because I'm going slightly fast maybe for them, I really encourage you to verify, go through and try to prove the things that I'm stating here, except maybe for the long theorems, because that will take more time. But things that are listed as examples, those you should definitely try to do. Mm-hmm. Because it is positive semi-definite, that means it's invertible. Hence, I can take its inverse. So let me. That's why I was. Maybe some people may call it strictly positive definite, but so for me, Okay, let's use a different color. That one? Okay, I can use that. So suppose A is a symmetric matrix. A is a real symmetric matrix. So Aij is Abi, and it is n by n in size. Then we say it is positive definite if x transpose Ax is strictly bigger than 0 for all non-zero x. And such matrices are invertible. If this is bigger than or equal to 0 for all x, not strictly so, then the matrix may not be invertible, and these are called positive semi-definite. So I'd like to reserve the word definite for things that are 0 if and only if the argument is 0. Because like I said, norms are positive definite. Several other functions are positive definite. So yeah. And the last one is just our friend, the indicator function. It's conjugate because, of course, that's the most we can do. We cannot solve it further. That's why it gets a separate name of its own. It's called a support function. You may see reference to support functions if you maybe in some other lecture also. But these are like some very classical basic convex functions with which we play when doing optimization. Here is another, I cannot resist challenges in the beginning, but later on I'll have to actually talk about work. But this is again for those who like to exercise their convex analysis skills that you have seen here, or this is a nice challenge exercise. X, Y, Z, etc. These are all positive numbers, scalars, and you can generalize this by inclusion exclusion to be a function of n variables. Try to prove that all of these functions are convex. It's an interesting task, and this is one of those tasks where things like second derivatives, etc., if you feel greedy to take second derivatives, will pretty soon show you that even for verifying convexity of some functions, no matter how many powerful tools, conjugates, indicators, whatever we see, it may not be easy. Okay, so now very closely related to the idea of Fenchel conjugate, which is essentially coming from the Max theorem that we had, is the idea of subgradients and the idea of duality. These two are together. So whenever you hear the word duality, there are several different kinds of duality that exist. For us, we may just think in terms of the Fenchel conjugate, we can just call it the Fenchel dual function. That is one thing we call duality. At other times when I talk about duality, you may think that originally we were talking about f of x. When we talk about duality, we may be talking about the gradient or subgradient of f of x. That's roughly the idea, what those nouns may mean. But let's look at subgradients. So as I mentioned, for convex functions, you can make these lines as tangents, which underestimate them. So important point is that we have this function curved up like that. At every point, we can find a bunch of lines, in fact an infinite number of lines that are globally underestimate the function. That means that are globally smaller than this function, right? So you have lines going all the way down there, and you keep coming up. The tightest such line is of course given by the tangent here, which is defined by the gradient. So that's for differentiable function. So already when I said the tightest such line, you should think in your head some kind of max is happening in there. And a line is just defined with a linear function. And you already saw that when we created the Fenchel conjugate, there was a linear function or something in there. So that's like high level how these concepts float together. The nice thing that happens with convex functions, that's one of the nicest things that happens, even if the function is not differentiable. So this is a smooth looking function, it's differentiable everywhere. We work with convex functions that need not be differentiable. They may look like that. They may have corners. So wherever it has a corner, it won't have a derivative. It will only have one-sided derivatives, as you have seen maybe in high school. And those one-sided derivatives have been very nicely and thoroughly generalized into the language of what is called a subgradient. So once again, the same idea. Even at a corner, now instead of having a unique tightest underestimator, you may have an infinity of underestimators, which are all global underestimators at that point. So the important point being, we are trying to get a dual view, and gradients prove so useful in ordinary calculus. And one of the cool things about convex functions and convex optimization is that many of the cool things you can do with gradients, we can extend those ideas to even non-differentiable functions. As long as they are convex, we can extend them with some with suitable notation. So here G1, G2, G3 are three of those tight lines that pass through there, so they are called subgradients. And that's a concept intimately related to the Fenchel conjugate, because each of these things you could think of as a line, and it's kind of the tightest possible line at that point. And some basic facts. I'll tell you some more stuff, important stuff about subgradients, and maybe I have to, well, let's not worry about acceleration so much, because subgradients are going to be important for us today and tomorrow. So some important facts. If f is convex and differentiable, then its gradient is the unique subgradient. And a vector, some vector g, is a subgradient at a given point if and only if this linear function is globally smaller than f of x. That means for any possible choice of x. So of y. So usually the nice thing about these subgradients is that typically if we can compute f of x, it's usually not too hard to compute one subgradient of f of x. And even though, as you've seen from my diagram, the subgradients are not really unique, the nice thing is because they satisfy this global underestimation property, that they give you this linear function that is globally smaller, it really doesn't matter ultimately, usually, which subgradient you pick when you try to use them. And many of the things that I'm saying right now, they will become more concrete once we start looking at actual algorithms that consume these convex objects. So determining, like I said, you may be able to pull out one subgradient, but if you want to characterize all possible subgradients at a given point, that is quite a difficult task, and usually we'll never attempt it, so we don't have to worry so much about that. And the development of subgradient calculus, which extends the rules of classical calculus that we by now take for granted, either the single variable calculus one sees in high school or multivariable calculus that you may see in undergrad, all those chain rules and compositions, monotonicity, etc. The things that we take for granted, almost all of them, not all of them, get extended to non-differentiable convex functions, and that is one of the major achievements of modern convex analysis, is to create that calculus. And this is Fenchel-Young inequality, which actually just follows by definition of f star. So I'll just rewrite f star in case it's no longer in your buffer, that f star of s was given by supremum of x so clearly by this definition, this inequality holds. And this inequality is also used repeatedly when doing convergence proofs and theoretical analysis of several convex optimization algorithms. And this inequality is really just a byproduct of the definitions. And this inequality helps us prove things like, if you want, things like Hölder's inequality and all sorts of things you may have seen in other places. Okay, so quick example of subgradients for those of you who have not seen such an example before. So I have two convex functions, f1 of x, f2 of x. I'm taking the max, so clearly by the max rule, the combination is convex. Assume now that both f1 and f2 are in fact even differentiable. So say I have f1 that looks like that, and I have f2 that looks like that. I take their max, which is then given by that part. What happened after we took the max? A kink appeared. It's not smooth at that common point anymore. So we had two nicely behaved differentiable, infinitely differentiable functions. When we took their max, at the common point, there is a possibility of non-differentiability showing up. It does show up because ultimately of a simple kind of reason, at a common point when you're taking max of two functions, we don't have a unique way to tell whether the max is due to f1 or is due to f2. That's pretty much what happens here. So here, at other places you may have be able to define gradients, but at that point you have several such lines which act as a subgradient. Hence, in the portion where f1 is strictly bigger than f2, then clearly the max is f1 and f1 is differentiable, so the unique subgradient is just the derivative of f1. Where f1 is strictly smaller, then the unique subgradient is just derivative of f2. Because I said of the property that if a convex function is differentiable, its derivative is the unique subgradient. And at the point where they are equal, you have essentially all these lines that turn around that point. Those slopes, which are here just real numbers, those happen to be the subgradients. So, so that's showing that we do like to take max, but max is in some sense one of the most non-smooth, non-differentiable types of functions that we have. Yeah, I will talk about that in a few minutes. That's a very important question because that's actually what you need if you want to do any programming with these creatures. So I'll just mention a brief theoretical thing here. Again, this part I'll just leave on the slides for summary. I thought many times, should I keep it in, should I leave it? Then I said, okay, for the benefit of the students, I'll leave this material in, even if some of it may be unfamiliar. So because we don't have a unique subgradient, there may be many subgradients, infinitely many. At a given point, all possible subgradients, the set of those subgradients is called subdifferential. And if f is a convex function, then the subdifferential set is nice. And for example, if it's differentiable, then that subdifferential set is a singleton containing just the gradient, and vice versa. So let's look at an example. So if f is the absolute value of x, this function is differentiable everywhere except at 0 where it has a kink. So it will have lots of subgradients there, and in fact this is such an easy function we can fully characterize its subdifferential at 0, right? So this is the subdifferential set. When you're strictly smaller than 0, derivative is -1, otherwise +1, and when you're at 0, all possible slopes, and here we know actually what the slopes are from -1 to +1, all possible slopes are our subgradients. So you have, so we managed to fully characterize that. This is one of those lucky circumstances where one can do this. Typically you cannot do this. It's too hard to determine that. Here is another example. I'll just leave it here because I'm not going to use it, but for this one actually even have the proof, but whenever it says an example, I actually am encouraging the students to please try to derive the proof yourself. To answer the, okay, before I answer your question about how to compute these, let me just give you, mention one thing. Typically, for convex functions, we do have subdifferential set does exist, means it's non-empty, but there can be circumstances where your function is defined, but the subdifferential may be empty, which means there may be no subgradient, which basically means to say there's no global underestimator. Here's an example of a function, because if x, the norm of x becomes bigger than or equal to 1, essentially you will end up getting a divide by 0, or you'll end up getting an infinity. So you the subgradient set is empty, subdifferential set is empty. So to answer the question, how do we compute subgradients? There is a little, that's why I said one of the achievements is creating a calculus to do subgradients, so that you start with something for which you know the subgradient, then you know that how to combine these things to get subgradient of the combination, and you develop addition, chain rules, and so on to be able to figure out. So I'll just summarize that list. I'm not going to go through that list, but I put it there for reference in case you need to compute subdifferentials later on for fun. So here is a summary of several of the rules. A star on those means that, you know, because these rules are for full general convex functions, they don't always hold as nicely as the ordinary rules of differential calculus, but for most of the convex functions that you will be working with in machine learning, these rules work without the star. And some of the most important rules are actually, if you, as we saw, getting a new convex function by taking a max over convex functions was a very important way of constructing convex functions. So one of the most important calculus rules is, if your convex function is created as a max, as happens when you have a hinge loss in SVMs or something, how do you construct subgradients, or you actually can describe the full subdifferential. So there is a rule for that. But I don't have time to go into these rules, but I'm leaving these here because these are very important chain rules to help you show how you can use this calculus to construct, to figure out how to do subgradients. I'll show an actual one example, which is interesting and crazy at the same time. So ordinarily, so that's the star. So if you had two differentiable functions, the derivative of the sum will be sum of the derivative, we are happy, fine. For convex functions, it can happen that the subdifferential of the sum need not equal the sum of the subdifferentials. This is a set summation, by the way. So it's one set plus another set, so which means combine all, make all possible combinations. So it can happen that this fails. But like I said, these are pathological cases, but one has to keep in mind. And if you've ever heard the word constraint qualification in optimization, that's essentially trying to ensure this doesn't happen. But here is an actual example, but rather than go into the example, again, I'm compressing for time because I want to tell you just a couple more interesting things. This inclusion always holds though. The creature on the right hand side is always included in the left hand side, but that's an important theorem, actually, it's Rockefeller's theorem. So even though, so typically a lot of the expected calculus rules do hold, many of the times these rules may break down, sometimes these rules may break down, and some of the times when these rules may break down happens usually when there are convex functions involved that can take the value plus infinity. So that's one of the common cases when this could happen. Or there is, or the subdifferential set of one of the guys happens to be empty or something. But most of the time you can just blindly do the subgradient. And another practical advice, if you are looking at a function, mostly you'll be the one who will be constructing the function. Just differentiate it as usual using your ordinary differential calculus, and then worry about the boundary case to figure out if you did it right. So that's the most practical way to get subgradients. So here is an example of the max rule, which uses several rules. This is the L infinity norm. So at 0, it has a gigantic number of subgradients. We have this subdifferential set, which is the convex hull, which I described long ago on slide 3 maybe, of basis vectors, the canonical basis vectors, which are just columns of the identity matrix, right? And to prove that this is the subdifferential set, just apply those calculus rules that I showed you. F of x can be written as, it's the maximum absolute entry of x. So for each entry you can pull it out by multiplying it with canonical basis vector and taking max of those. Well, this is just absolute value, and this is a linear transformation. So you can use the chain rule and the max rule, and you saw that the partial, the subdifferential of the absolute value function, what it is. Putting those 3 rules together, you can get the full subdifferential here. Means this is just an exercise showing you that even for this trivial looking function, I had to actually invoke 3 of those rules or theorems, but fine. So let's just do a concrete example of that. So suppose f is defined as a maximum over affine linear functions, finite number. How do you want to pull out a subgradient? This is pretty close to essentially, if you had that hinge loss type of thing and you want to compute a subgradient because you're trying to do optimization, how would you do it? Well, this is a max over some finite number of terms. The max rule says, let me actually painfully point out the max rule. The subdifferential is convex hull of the subdifferentials of all the active functions. So when you have a max over several functions, one of those guys will end up attaining the max, as we saw in the max example. And this is just trying to say how to combine their individual subdifferentials to get the net subdifferential. So this is a very important theorem. In its full generality, it is still a research topic to fully characterize this theorem. That's why there's a star there. So this exists, but in full-blown mathematical generality, it's still non-trivial activity. Anyhow, so this is one of the functions fk. Suppose that f of x, suppose k is some index for which f of x is this. That means the kth function is active. Well, here actually the kth function is differentiable, so its subdifferential is just that singleton set. So you collect all those guys, take their convex hull, that is the subdifferential set, but we don't want just the whole set is too difficult, you just wanted to pick one subgradient, so just pick some member from that set. And AK would be one of those members, right? I don't know exactly what Danson's theorem refers to, but the max rule is for finite index. There might be a soup there, and you may have uncountable index set, but even with that things work out, but there are some other subtleties that happen. So this allows you, so what was the plug and play here? You have a max over several functions, see which of those functions attain the max, take its derivative or subdifferential, pick one of those guys, and that's a valid subgradient. So that's a very easy way to pick subgradients. Another thing which we'll see actually tomorrow is if f of x is given by summation over infinite number of things, which is called integration, it's written as that integral, and each of those f of x comma u is convex in x for every u varies over some space, whatever, it's just you add those things up. Then one way to pick, all of these things require rigorous proof, okay, and I'm not going to do any of that here, I'm just telling you that these things exist, and most of the time the thing that you would intuitively expect does hold with the caveats. So for each u, you can pick any subgradient of this function. So we are just applying the summation rule of subgradients here, because this is just a summation. Then the integral of all of those separate subgradients is going to be a member of the subdifferential. So basically that means you can, even when you have a sum of an infinite number of objects, you can still pick out a subgradient from them, as long as we can of course compute that expectation. And this thing is kind of abstract right now. Tomorrow I'll show you how this thing is at the heart of very profitably doing optimization in machine learning. Okay, so now I have, because I told you in the beginning I'll take some more time, I'll use maybe 10-15 more minutes. Finally, we have managed to, after constructing basics of convexity, reach optimization problems. And I just want to mention one important concept within optimization problems, and that is of duality. So let's quickly go to that. So I'll just give you some notation, right? So you have some, this is a standard nonlinear optimization problem. Cost function, constraints, and domains of the function. So for us, whenever I say domain of a function, by that I mean the subset of r to the n over which my function is finite. That's usually what is domain. So I'll just drop that there are domains. Those are implicitly in there, but they are there. So if the FIs are differentiable, then it is called a smooth optimization problem. This is just the nomenclature we are using. If any of these FIs is non-differentiable, then it's called non-smooth optimization problem. So one more difference to pure math. In math, when people use the word smooth, they mean an infinitely differentiable function. In optimization and machine learning, when we say smooth, we just mean once differentiable. Big difference, but for optimization that suffices. If all the FIs are convex, we have convex optimization, otherwise you have non-convex optimization. Pretty simple, right? And if there is no cost function, or if there are no constraints, so if there is no cost function, it's called a feasibility problem. If you just have the cost function, no constraints, it's an unconstrained problem. But that's just the standard stuff that you have seen. And if you have feasible, so if X is the feasible set where all constraints are satisfied, then the optimal value possible over that is called the primal optimal value, denoted as P star. I'm following notation in Boyd and Vandenberg's book. And some interesting things to note about optimization problems. The reason I'm mentioning this here, sometimes it has happened to me that I start out with an optimization problem and it turns out it's really hard to tell, does this thing even have a solution? Most of the time, for machine learning models or models in statistics, people don't worry about existence of a solution because it follows rather straightforwardly. But when you are exploring new mathematical models, creating new cost functions, you should worry a little bit about first being able to say, does my problem even have a solution before I try to do anything, right? Here's a quick example. So if the feasible set is empty, the problem is infeasible. There is no solution. You have contradictory constraints, right? Could happen. And by convention, we say the infimum is plus infinity for infeasible problems. It's an important convention. For example, if you can have problems that don't really have a solution, that means you have an inf, but you don't have a min. There is no actual vector or scalar x that actually attains the solution. For example, if you're trying to minimize x, there is nothing else. There is no solution to that problem, right? It's unbounded below. So sometimes minimum might not exist. One has to think about it. Anyhow, so the nicest thing about when doing optimization with convex functions is, one of the nicest things is that for a convex function, given the way it is curved up, just looking locally around you suffices to tell you how the function behaves globally over the entire space. That's what makes gradient-based optimization and subgradient-based optimization, the kind we are looking at, very easy and popular. Because a gradient, by its very definition, is a very local first-order concept. So for convex functions, that's a rare distinction, that local information suffices to do global optimization. Okay, so some of these theorems are easy. I want to, let me actually, rather than show the easy theorem, let me show you, I'll show you an application of, again, the subgradients. So if you have constraints, you have a feasible set X and you're trying to optimize, you need some way to detect, have I solved the problem, right? So that means you need some way to characterize optimality. And that's a very big topic, how to characterize optimality. Using gradients to characterize optimality is pretty much what we'll do. So if f is convex, it satisfies that inequality by definition. So if this holds, then x star has to be optimal by construction. The other direction I'll quickly show you on the next slide. And if this is non-negative at x star an alleged minimum for all feasible y, well, if there are no constraints, that means the entire real space is feasible, then the gradient had better be 0 for this inequality to hold. So you recover the ordinary condition that gradient has to disappear for unconstrained problems to have optimality. If the problem has constraints, then of course clearly the gradient need not be equal to 0, but it has to have this, has to satisfy that inequality. And let's prove that inequality using something that is called Fermat's rule. He didn't write it in this notation in 1600 something, I'm giving him that credit. So this is usually called Fermat's rule, and this yields for us that optimality condition as a byproduct of just our definitions. That's the nicest thing about it. So suppose f is a function, convex function, let's say. Here it need not be convex, but say it's a convex function, which can take the value plus infinity also. So we say the set of minima of f, the actual x's that give you that minimum value, that's called the argmin set, is the set of x's for which subdifferential of x, f at that x contains a 0, which is another very nice thing. Gradient having 0 was our standard way of detecting optimality for differentiable functions. Using subgradients rather than gradient, we have the entire subdifferential set. If 0 happens to be a member of the subdifferential set at a point, then that point is optimal. So it very naturally generalizes. That's the beauty of it. So here's a proof of this by definition, right? So if x is a minimum, so fx is less than fy for all y, right? That means fy plus fx is bigger, fy is bigger than fx plus 0. Hey, but this looks just like the definition of subgradient, so 0 is a subgradient. Vice versa, if 0 is a subgradient, then by definition you have that inequality. So 0 belonging to the subdifferential is characterizing global optimality for convex functions. Proof by definition, right? I didn't prove anything, I just wrote down the definition. The only thing that we proved here is, used here is that 0 multiplied by something is 0, but okay, that's easy. So the benefit of that notation, that previous proof which is usually given using all sorts of geometric arguments, which are good for people who can do geometry, I cannot. I like this simpler argument here, is suppose now we are looking at constraint problems. You're trying to minimize f of x over a set x. One way to do write that problem as an unconstrained problem is to use my favorite function, the indicator function, fx plus indicator of x. Because this function expresses severe displeasure when you're not in the constraint set, it becomes infinity. The only way to minimize this is to make sure that a point x that you pick lies inside the set x. Hence, this is another way to write that constraint problem as an unconstrained one. And now, the rest probably you may guess what comes up next. I showed you that optimality is characterized by 0 belongs to subdifferential. I took a constraint problem, wrote it as an unconstrained problem. Now just compute its subdifferential. So minimizing x has to satisfy that. And that should have been f, not f naught. And that means you do. So here is where some kind of constraint qualification comes. Please ignore it for now. The real thing to appreciate in this proof is I took a constraint problem, wrote it as an unconstrained problem using indicator functions, and now I want to characterize an optimality condition for this unconstrained problem. This unconstrained problem involves f plus an indicator function. So using my subdifferential calculus, I try to characterize the subdifferential of the sum of these two functions. And so we assume we know what is subdifferential of f, it's whatever, and then we need the subdifferential of the indicator function, which is also a function, sometimes plus infinity. So to construct its subdifferential, I cannot give an explicit form of that because that will depend on what the constraint set is. You just invoke the definition. A vector g will belong to that subdifferential if and only if this happens. Well, so belonging there means that x belongs to the constraint set and 0 will be upper bound, because if y is in the constraint set, the left hand side becomes 0. So that's really just exercising definitions. And because we don't have anything else, so usually this is the common trick in mathematics, right? If you don't understand the concept further, give it a new name and carry that name along. So we give it a new name. It's called normal cone. It has geometry behind it. That's just the subdifferential of the indicator function. Fine. With that jargon, let's look at an application, getting an optimality condition for differentiable convex functions. You want to minimize f of x. If f is differentiable, that means 0 should belong to subdifferential of that, which is just the gradient, plus the subdifferential of the indicator function, which is called normal cone. And you do plug and play. The normal cone is defined by that, right, equation. So you end up recovering the optimality condition of differentiable convex optimization as a byproduct of merely exercising the definitions. So the only non-trivial thing that happened here is the one that I didn't speak about, is some assumption that authorizes you to do the rest of the calculus. So this may appear obtuse or maybe not the obvious way to detect optimality to everybody, but I think it's an achievement of being able to define good concepts and notation so that something which would previously be a theorem is just a byproduct of the definitions. So I think I should stop now. I will actually then use 15 minutes of the next lecture to talk about duality before moving on to using all those concepts to actually start doing optimization.